Okay, everybody, we're back with expected value and game theory. We talked about dominance last time, and now we're going to talk about what happens when we can reduce by dominance, but maybe not all the way to a pure strategy solution. What if there's more than one strategy active in the final analysis? And that's when we use expected value. And expected value is much the same as it is in probability theory. It means the average value when we play the same probability experiment or the same matrix game over and over and over. And the players' strategies converge to an optimal setting, let's say. But we have to know how to calculate expected value first. So remember that we take the outcome times the probability of that outcome, and we do that for all outcomes x sub I in the probability space. Well, here we're going to do much the same thing, except that our x sub i's, they're the outcomes in the matrix game, and the probabilities are the proportions which the other player plays their strategies. And you'll see how that works in just a second. So here's our first example. Okay, so we're going to evaluate the expected value of Rose strategy A and expected value of Rose strategy B, given that the optimal strategy that Colin plays is, oh, notice the first one is 0. Well, let's talk about that quickly before we continue. Right, there's dominance here. So we want to start the process by reducing by dominance as far as we can and then calculate expected values. Why? Well, the rational play principle says that Colin won't play a dominated strategy. And since 0 is less than or equal to 8 and -4 is less than or equal to -4, Colin's strategy A is dominated and therefore he'll never play it. And therefore we end up focused on a sub game, just this 2 by 2 sub game after we eliminate the strategy A when we're calculating Rose's expected value. Okay, and remember, Colin is minimizing, but here we go. We know, right, that Colin plays 3/4 B and 1/4 A. And if Rose knows that, she can calculate her expected value, right? What do? Well, we take it piece by piece. She plays strategy A, and then she gets the outcome 0. How often? Well, however often Colin plays B. Okay, so that's going to be C2. In other words, this vector here, C is a vector, C1 is the first component, C2 the second, and so forth, right? So C2 times the outcome of 0 times C3 times the outcome of, plus C3 times the outcome of -3. Okay, that's the expected value formula. I just take the outcomes times the proportion of time Colin plays that particular column. All right, and so inserting what these values actually are, C2 is 3/4 or 0.75, C3 is 0.25, and again, this whole thing is 0, right? And I have -3/4 here or -0.75, just following through the calculations. And those are Rose's expected values. That's Rose's expected value for strategy A. To look at strategy B, we do much the same thing, right? You'll notice that Colin is still playing strategy B 3/4 of the time, and when he does so, Rose gets the outcome of -4, and Colin is playing strategy C 1/4 of the time, and when he does, Rose makes 4. So 9 times 1/4, that's 9/4 or 2 1/4. -4 times 0.75 is -3, so I have 4 1/4. Wait, that doesn't seem right. 4 1/4 minus 3. I'm gonna have to think about that, right? um, 3/4 times -4. The 4's will cancel. That's -3 and 4 1/4. That doesn't seem right. Let's take it to the notebook and double check things there. Okay. So the notebook has our definition of expected value all right there. Let me get rid of the stray marks. Okay. And the expected value of rows B, and I will show these so that you can see the correct notation to use, you've got to make sure that you're in markdown mode, right? And why am I doing the text rows space A? Well, it just looks a lot better when I'm in equation mode, but I'm typing a word that I want in English, it's not mathematical symbols, right? I use text. Why? Well, otherwise it's going to appear kind of italicized and variable-like, and this way it's going to present as the actual text like I want it to. Is it the biggest deal? No, it's going to make it look a little nicer. It's visual preference here. And what do? We do 0 is the outcome, the 3/4 is the percentage of times it gets played. Then we have -3 is the outcome and the percentage of times it gets played. So the expected value of rows A is -3/4, and the expected value of rows B, again, this is where I was pointing out that the -4 and the denominator cancel, so I'm left with a -3, which is also -12/4, plus 9/4. Oh, okay, so if it's plus 9/4, then the overall is -3/4. I'll have to look and see what exactly was wrong on the slide, but this one's correct. Excellent. So that's how I calculate Rose's expected values. It works the same for Collins, except we need to know Rose's strategy mixture, and then we'll proceed down the columns for Colin. All right, let's try an example of that. Okay, so here, first of all, we have to verify there's no dominance, right? Because every time we start one of these matrix games, we want to look for dominance. Why? Well, the expected value calculations aren't as accurate, and sometimes they're not accurate at all if we have these inactive strategies included in our expected value computation. So we want to avoid that. But here we have Rose's strategy mixture, and this should be, it's supposed to be the vector C. I had a typo there. Supposed to be the vector C, so we have Collins strategy mixture. I am not alleging that these are optimal strategy mixtures. I'm just saying we're going to assume that that's what they're playing so that we can calculate some expected values. All right, and so what do? Notice for rows, right? For rows A, 9 times the percentage of times that A gets played, that's 9 times 0.2, and then 0 times whatever, right? It doesn't really matter because 0 times anything is 0, and then the 0.5 times the outcome of 4, right? And when you multiply that out, add them up, that is 3.8. I have 1.8 plus 2, which adds to 3.8. And the similar calculations will help us see, right, that I have 0.2 times 5 plus 0.3 times 11 plus 0.5 times -2, which comes out to 3.3, right? And I have 0.2 times -1 and 0.3 times -4 plus 0.5 times 12, right, which comes out to -4.6. And you can verify those calculations. Let's jump to the notebook and see. Okay, here's our example 2, and I have all of them. And what I want to show you right now is the align format, right? So begin align, and then we have to end the align, right? So end curly brackets align, and then I'll put my $sign. So now I've opened it and I've closed it. And what does the align environment do? It allows me to put these 3 equations in here. Let me just copy them. I'll leave them as they are in case we mess up. Okay. Now, first of all, we've got a bunch of $signs that we don't need. Okay, so I'm going to delete the $signs out of the interior. I do need them wrapping the entire environment, but I'm getting rid of those. Okay. Now, the first thing you need to know is that I have to separate lines in the begin environment with the double backslash. And this one's optional. Do I have to end the final line? Not really. Okay. And this is going to work except it doesn't know where to align it, right? So I have to choose a symbol and I put the ampersand before that symbol. So I'm going to take the ampersand and put it before the final equal sign of the two in all three rows. And then, and why is it invalid syntax? I hadn't yet put it in Markdown. So I put it in Markdown mode. And now it's presenting all three of these together and aligned. Okay, and by the way, you can align them. If I put the alignment character, in by this equal sign, it would line up these three equal signs. You can put it on an operator. You can put the alignment character anywhere you want to make it align how you think is most visually appealing. It's somewhat dealer's choice there with how you'd like to present it. All right, so that's Rose's expected values. What about Collins? Okay. Well, now we've got Rose's strategy mixture. Again, not necessarily optimal, but that's what she's playing. So how do we do that for Colin? Well, for Colin, right, we take 9 times 0.2 and then 5 times 0.5 and -1 times 0.3 because we know the strategy mixture that Rose is playing. And so that calculation, when we do it, looks like this, right? And just like I said, we have the 9 times 0.2 and the 5 times 0.5 and it's a -1 here, so the negative's out here. Here's the 1, here's the 0.3, and I have 1.8 plus 2.5 minus 1.2. So let me think about this. 1.8 minus 1.2 is 0.6, so 2.5 plus 0.6. I don't think I have this one right yet. I have 1.8 minus 0.3, that's 1.5, plus 2.5, which is 4. Sorry. Trying to do that arithmetic in my head really quickly was not working, was it? But again, when I'm evaluating column B, right, I have 0 times the 0.2 in the first slot. And notice that these proportions are the same all the way down. So I can make good progress by copy pasting. I have 11 times the 0.5 and I have -4, right? This -4 times the 0.3. So I have 5.5 in the middle. I have 0 at the beginning, so 5.5 minus 1.2 is 4.3. And the final expected value for Colin will be the same, will be calculated in the same way. Okay, so let's jump over to the notebook. And what am I going to do? I am going to come down here to where I have the align environment already created, and I am going to put that in. And this cell is already marked down for me. Okay, and you can see the same values from the slide. And let me open this back up so you can see how I've done the align environment. It has to be enclosed in double dollar signs. Well, the double dollar signs just makes it centered. If I just close it in dollar signs, single dollar signs, it'll do the same thing, but it will left justify the block of equations. But let me go back to the double dollar signs. And notice that I've done a little differently here. The alignment character is by the first equal sign instead of the second. So now this one's aligning a little more left justified. Again, it depends on what you think is the important information in the set of the equations and what you want justified and easy to see. I honestly prefer it the way we did it for rows, but I wanted to show you that that's how we can do it. The closing of each line, I end each line with a double backslash. Notice that I ended the final line with a double backslash, and it does not cause a problem whatsoever. That is helpful to know. And again, notice the left justification for Colin, whereas I have the right justification for Rose. Again, that has everything to do with where I put these alignment symbols, that ampersand symbol. All right. So again, hopefully that is enough. And if you need a little more time to look at the coding to see how the $ mathematics, the LaTeX equation goes, you can back up the video and pause it. Let's jump to example 3. Now, example 3 is interesting. Why? Well, because when we start reducing by dominance, it takes about 5 seconds to realize, oh my goodness, Rose has a strategy with a lot of large positive values in it. And when we start to look, we're like, oh, 8 is greater than 7, 11 is greater than -1, 12 is greater than 5, 12 is greater than -3. Oh, B dominates A and B dominates C. Oh my, and B dominates D as well. So it turns out that Rose will never play C or D or A by the rational play principle. So she'll only ever play B. So what's Colin to do? Well, he's going to minimize, right? Remember, in these zero-sum matrix games, we can simplify it by only showing Rose's values. Colin's are the opposite. So he can make either -8, -11, or -12. He has two ways to make -12. And of course, since he's minimizing, he's going to choose the 8. And so we know that the game is going to have a pure strategy solution at Rose A, Colin B. Sorry, I did that backwards. It's Rose B, Colin A. Right, so Rose B, Colin A. And the game value will be 8. We'll write it in terms of Rose's game value for the moment. All right. And when we get to non-zero sum games, we may have to specify different values because they may not be opposites. But in this case, we're golden. All right. So that one reduces by dominance. And a couple quick points. I have mentioned this earlier in the video, but I want to make it clear. We always start reducing by dominance. Any matrix game we look at, even if we know we're going to have to do something later, we start by reducing by dominance as far as we can. There may be no reduction by dominance possible, but we check before we calculate expected values because the expected value calculations will be thrown off by including inactive strategies. Okay, so we're going to make a mistake. And as you see, what do I mean by inactive strategy? I mean in the final assessment, Rose only will play B because everything else is dominated. Right? So these three, A, C, and D, are inactive strategies. Why? Because Rose's optimal strategy mixture is going to be 0% of the time play A, 100% of the time play B, 0% of the time play C and D. So where I have zeros in the strategy mixture, those are inactive strategies. By the rational play principle, Rose is ignoring those strategies as if they didn't exist. And if I include an inactive strategy in my expected value calculations, I will make a mistake, almost certainly. Okay, so I'll be back to talk about next time how do we use expected value and equalized expectations to find a solution to a game that doesn't have a pure strategy solution.